Got it. All right, welcome everybody back to the latest in our fall colloquium series of distinguished alumni in recognition or celebration of our 100th year as a department. Today's speaker is Professor Britt Lundgren, University of North Carolina at Asheville. Britt got her PhD in 2009 with Robert Brunner, working on quasar absorption lines in the Sloan Visual Sky Survey. She did a postdoc at Yale and had an NSF postdoctoral fellowship at Wisconsin before doing a one-year AAAS Science and Technology Policy Fellowship at the National Science Foundation, where she got to see how the sausage is made. And then in 2016, since 2016, she's been a professor at UNC Asheville. And I'm happy to report that just this year, she's been promoted to associate professor. So Britt will tell us about the gaseous halos of galaxies at high redshift. Please take it away.
So thank you, Paul. And I want to thank all of you for the invitation to come back. It's a real privilege to be considered a distinguished member of the alumni from this great department. And it's a real treat for me to come home. I'm an Illinois native, so it's nice to venture out of Appalachia for a little while, come up here, see how the department has changed over the past 10 years and get to talk to a number of you and hear what you're up to. I especially enjoyed having lunch with the grad students today, so thank you all for hosting me. Right, so let's see, I will jump right in. If I can, it's a little, I feel like I've missed a trick with the Zoom menu staying on the screen. But unless it bothers you, I'll just go with it. Okay, so what I'm going to be talking about today generally is the topic of galaxy evolution. And of course, I'll be talking about how galaxies evolve from the perspective of the gas in their circumgalactic medium. But let me just step back a bit and show a familiar plot that is now kind of canon in observational astronomy and cosmology in particular. What's shown here is the cosmological evolution of the volume average star formation rate of the universe. So this is that famous Maddow plot shown here in a relatively recently updated plot from 2014, showing how on average, stars are being produced with increasing rates up until around redshift 3, at which point things kind of top out and then begin to decline. So these rough periods in the observable redshift range where we have good data about galaxy star formation rates are kind of generally categorized into 3 major periods, which you might hear referred to as cosmic dawn, cosmic noon, and cosmic happy hour, as Rachel Bezanson recently coined, and I like it. So we'll stick with that. It's a little less depressing than some other possible terms for our current epoch. So we know all of this after decades of combined observations and a lot of hard work, following up on galaxies that we see in these deep legacy multi-wavelength fields. So of course, the most famous of these is shown here, the Hubble Ultra Deep Field, which contains about 10,000 galaxies, which extend up to about redshift 8 or 10, depending on how many galaxies you need in your sample. And recently, a portion of this particular small survey field has been followed up in the extreme ultra deep field, where we have even deeper multi-wavelength data. So one of the first projects that I worked on after leaving Illinois, when I was working with Peter Van Dokkum's group at Yale, was to take the 2009 updated ultra deep field data and make a deep photometric catalog of all of the galaxies that could be extracted from that single image. So I spent about 3 years working pretty hard on this one small section of the sky, and feel really privileged to have had that opportunity. to work with some of the first data coming out of WIF-C3 in this particular spot of the sky. So what I did during that first project was to create a detailed photometric catalog from which SEDs could be extracted for the galaxies, masses and star formation rates could be determined. And one of the first results was I was able to make a mass function at different slices in Redshift, only using galaxies in this one particular field on the sky. So looking at how the mass function evolved over time meant that I could also select samples of galaxies at constant cumulative number density and actually try to trace how similar types of galaxies were changing in terms of their stellar masses and their star formation rates over the span of Redshift 8 to 1, again, just in this one small region of the sky. And so that's the inset that's shown on the right. Each of those color-coded plots is a different sample of galaxies with a different cumulative number density. All of them show the same kind of basic shape, where as you move from high redshift towards cosmic noon, you see a ramping up of the star formation rate, and then a steep decline around redshift 2. Now, the exact point at which those different inflection points occurs does depend on the halo mass of each of those samples and indicates the presence of what we now sometimes refer to as cosmic downsizing. But forget the details, I'm just showing you this to make the point that using the ultra deep field and other legacy multi-wavelength fields like Cosmos, GOODS, the deep field and UDS, we're able to really trace out how galaxies are evolving in terms of their stellar mass and their star formation rates from pretty high redshift to the present. Now the question is, of course, what is actually causing those trends that we see, right? This ramping up of star formation and then the steep decline around redshift 2. Well, our fundamental understanding of galaxy evolution indicates that star formation is going to be dictated by the presence of gas and the properties of the gas available to these galaxies. And we also know from the past few decades of observations of the Milky Way and other local galaxies that the visible part of the galaxy that we can see clearly in those ultra deep images is really just the tip of the iceberg. The luminous stellar component of the galaxy is just about 1/10 of the size of its inner circumgalactic medium. And each of those galaxies has an extended halo of gas that extends out to 150 kiloparsecs or beyond, depending on the halo mass. And the amount of gas in the halo is not inconsequential. We now know that there's approximately as much mass locked up in the gas as there is in the stars. And this, of course, is the reservoir that galaxies presumably are drawing from in order to sustain their growth through star formation. Now, the gas in the circumgalactic medium, as I'm sure you're all aware, is not only abundant, but it is also dynamic. And so we observe in our own Milky Way accretion of intergalactic gas onto our galaxy, replenishing the fuel for star formation. We also have the presence of galactic fountains powered by dense clusters of supernovae going off in reasonably short amounts of time nearby to one another. And not shown here, of course, we also in most galaxies can assume that there could be some feedback from an active galactic nucleus at the center. And each of those kinds of dynamic processes will influence a galaxy's ability to form new stars, okay, due to the moving of gas and the heating and cooling. So in addition to all of those processes, we also know that galaxies are constantly merging. And so you do have also the contribution of tidal streams from satellites that are interacting with the halo of the more massive host galaxy. We see evidence of this in our own Milky Way. And when possible, we resolve this around other galaxies in the local universe as well. So that's the basic observational paradigm from local galaxies, including our own. But we also have at this point very mature numerical simulations with highly complete physics and detailed resolution, which can show how the dynamics of this gas plays out over the course of billions of years of a galaxy's evolution. So this is a really nice visualization from Rob Crane and Jim Geach of the Eagle simulation, showing how a galaxy like our own Milky Way forms through the accretion of gas from the intergalactic medium over the course of billions of years. And the difference in those two panels was metallicity and temperature. And this is a pretty dated slide. I've had this in my talks for some time. So those of you who work on simulations will know that we now have many players in the detailed galaxy evolution simulation game. But early on, Areco and Gadget were two competing simulations. And I'm showing them here just to make the point that each of these numerical simulations has slightly different methodology and resolution and initial parameters. So by using each of them to make predictions, we then have something to look at in our observational data and try to determine which model is most like the real universe. One of the most recent snapshots from one of the latest, greatest simulations from illustrious TNG is shown here. So this is a figure from Dylan Nelson et al.'s paper from 2019, showing a disk galaxy edge on, and this is a star forming field galaxy at about Redshift 1, something similar to what our Milky Way might look like in the past. And what's really nice in this visualization is that the direction of gas flows is indicated with arrows. And what you can see is that perpendicular to the disk of the galaxy, you have outflows rising approximately perpendicular. You also have accreting gas coming in along the major axis of the galaxy, and some galactic fountain activity that extends out to 50 kiloparsecs, approximately the virial radius of this galaxy. So we really do finally have really precise simulations that we can hopefully try to test using observations from the real universe. Now, of course, this is tricky, right? We have detailed observations of our own galaxy because it's close by, some of the nearest neighbors as well. But once if you really want to test these models of evolution of galaxies spanning billions of years, you need a way to observe what's going on with the gas in distant galaxies. And this is challenging because that gas is diffuse and it's not very luminous. And so one of the best ways to reveal that gas at all is through absorption. So backlighting studies using quasars have been in existence since the 60s. And we've been using quasars to illuminate gas around foreground galaxies, really since the 90s in a more complete way. And the reason we do this is because quasars are, brighter than normal galaxies. We can see them from farther away, so they're better at backlighting distant things. The disadvantage, of course, is that they're very sparse. And so some people, in order to get around this, have used bright galaxy populations, like the Cosmos sample, for instance, to have galaxies backlighting galaxies. But the problem then is that those galaxies are not as bright. So if you can use quasars, you'll get the highest signal to noise measurements of the absorption using them as backlights, but you're unlikely to find one behind your favorite galaxy. And even in these deep legacy galaxy survey fields, there tend to be very few of these bright quasars simply because they're so sparse. So nonetheless, if you do have quasars backlighting a galaxy, this is highly valuable information, because the absorption line information that you get in a quasar spectrum can give you all kinds of information about where gas is along the line of sight. And if you have sufficient resolution, You can also measure the composition, temperature, and kinematics of that gas as well. So this makes, backlighting experiments extremely powerful for detecting and studying all of these gaseous processes that we think are driving galaxy evolution. So outflows, inflows, tidal stripping, etc. So one of the most prolific absorption line systems that has been studied, ad nauseum by people who work in the circumgalactic medium of intermediate and high redshift galaxies is magnesium-2 absorption. So there's nothing particularly special about magnesium-2 absorption other than we find a lot of it when we look at distant quasars. It's a common byproduct of star formation. We think it's present in galactic winds, and it's observable over many decades of hydrogen column density, making it detectable in many different environments. We've known since approximately the late 80s, early 90s, that these magnesium-2 absorbers are associated with luminous galaxies, but it's been difficult to build up large samples of magnesium-2 absorbing galaxies simply because typically at the redshifts where we can detect these things, it's very difficult to directly detect the host galaxy that has produced this gas that we see in absorption. Nonetheless, in optical spectra, like what we get from the Sloan, you can detect magnesium-2 over a very wide redshift range, about 8 billion years of cosmic history, spanning redshift 0.35 to 2. It also makes a really easily identifiable doublet, which makes it stick out like a sore thumb when you see it in a spectrum, even at low signal to noise, which has made it possible to build up very large samples of these absorbers, which should be tracing all of those same processes that, that play a major role in galaxy evolution. Yes?
What's the fainter line to the right of the double?
Oh, that's magnesium-1. This is just a cartoon. Yeah. Normally, you would also see iron lines accompanying the magnesium, but I just took a composite absorber and just kind of faked it there. But yeah, usually if the magnesium-2 is strong enough, you get not only that doublet, but a magnesium-1 line as well.
But it is common to see multiple systems in the one cell.
Yes, yeah, about in the Sloan, about 1 per unit redshift is what you'll see along your path length. Yeah, and the better your signal to noise, the more likely you are to see something, because there are many, many more very weak magnesium-2 absorbers than very strong ones. Okay, so the sample that I've been working on since I was here, and actually even before I was at Illinois, I was at University of Chicago for my undergraduate, where very early on, I replied to an ad to get involved doing undergraduate research on the early data release. So I've been doing this for 2 decades now, working on the quasar sample from SDSS, which has been just a real privilege and a lot of fun. And so I have been a part of the SDSS through all of its generations, and I'm now finally out for Sloan 5, unfortunately. But in Sloan 1 and 2, this is where we built up the legacy sample of about 107,000 quasars. In Sloan 3 and 4, the BOSS and EBOSS survey would continue to build up the spectroscopic quasar sample, pursuing fainter, higher redshift quasars with the goal of measuring the baryon acoustic oscillation feature in the Lyman alpha forest. You know, we now have more than 400,000 quasars in the full Sloan survey. Some of them have multi-epoch data, which is interesting for other purposes. But fundamentally, I see these as core samples of the universe and have been working for some time in a small collaboration to refine an automated pipeline for extracting those patterns of metal lines, each of which should be probing a galaxy which is otherwise too faint for us to detect. So I've continued working with Don York over many, many years, and also with Varsha Kulkarni at South Carolina and Yusra Al-Sayed, who's the data pipeline manager for LSST now at Princeton. But this has been a really fun project, and we now have a really, really nice pipeline, which I have some students running now on the full data release 16 quasar sample. So in total, we have something like 200,000 individually detected metal absorption systems. Again, like I said, these are essentially galaxies that are not otherwise detectable in the Sloan footprint. And this is just showing you that whole composite magnesium-2 spectrum that I was referring to before. So normally, you know, you'll see that doublet in magnesium-2 because it's the strongest line. But if the system has enough column density or velocity dispersion, so that it's a pretty strong feature, you'll probably also always see those iron and manganese and magnesium lines as well. We do also look for high ionization lines, so carbon-4, silicon-2, silicon-4, aluminum-3, kind of all of the lines that we can. And so we're in the process of now publishing this very comprehensive catalog of multiple ions, which is a little different from other catalogs you may have heard about, which really are just triggered by doublets of magnesium and carbon. So ours is a little bit more sophisticated, we think, which is why it's taken us so long. All right. Oh, yes.
Well, are you gonna say, can you just say a few words about how you actually run that through? You
Yeah.
construct a template?
Yeah, so what we do really, it looks like, I mean, a clever way to do it might be to just run a template, do a Fourier transform. That's not what we do. So we actually continuum normalize the spectrum first, and then scan through the entire spectrum looking for significant absorption features. And once we have a list of all those significant absorption features, we look for doublets with the characteristic separations of magnesium and carbon. Once we have something that matches the right wavelength separation, we determine its redshift and then look for all of the other lines we might expect. And of course, this produces overlapping identifications with different probabilities. And so we then run some machine learning on the output to refine it and give a confidence score for every single one. So that's the nutshell version. Yeah. And it's supervised machine learning. So we've done a load of visual inspections to pick out the places where the pipeline regularly fails. Okay, so with these enormous samples, we can now, sorry. Oh, does this drive everybody else crazy? I don't know how to. No, okay, sorry. So with these large samples alone, you would think that we could do a lot of really great science about the circumgalactic medium of galaxies at intermediate and high redshifts. But of course, the problem is it's actually much easier to detect this gas in absorption than it is to detect the luminous component of the galaxy that hosts it. So if you look at one of these magnesium-2 and iron observers that we pick up in the Sloan above redshift 1, it's very clearly there. We have virtually 100% confidence that what we're picking up is real. And then when you look to the Sloan imaging, all you see is a fuzzy PSF of a quasar, right? So we have no chance of detecting the galaxy that goes with that, with the imaging that exists in SDSS. Now, if you have an HST image, it's a totally different story. So this is one such image of, I think, that exact same Sloan quasar as observed in the F140 band with WIF-C3 on Hubble. So what you can see there to scale is that there are a number of clearly resolvable massive galaxies at very close impact parameters to the quasar, none of which are really easily observable with the imaging of SDSS. Now, at that redshift where we detect absorption, you can draw a radius of 60 kiloparsecs where you would reasonably expect metal-enriched gas to be associated with a galaxy. Beyond that, we don't usually expect such strong absorption features. And still, there are 4 galaxies in that radius. And unless you have redshifts for those galaxies, you're hosed again, because you would really just be guessing which of those belongs to your absorption system. Okay, so this is not a new problem. This has been the problem in quasar absorption line work for decades. And even with those very large SDSS samples of absorbers, tens of thousands in number, that problem was not resolved. So during the time when I was here working on my PhD, people were just starting to use these very large samples to do statistical work to say, what can we learn about the host galaxies of these absorbers without actually detecting the host galaxies? So some statistical tricks that were utilized were things like large scale clustering measurements, just the three-dimensional distribution of where those absorbers are found in space. And also stacking. So stacking the images of quasars that have absorption detected in their spectra and looking at their residual light, making an SED of that light and trying to estimate the typical star formation rates of the galaxies that were contributing to that absorption. So I won't go into detail on all of those studies, other than to say that they all converged on a general result that this magnesium-2 absorption correlated with star formation in galaxies. You would see excess blue light around quasars that have foreground absorbers with strong magnesium-2. You would also find excess O2 emission and excess dust reddening in the spectra of those quasars when stacked. And so all of these things pointed to quasars backlighting, maybe an outflow from a star-forming galaxy, but none of them, again, were using direct detections. And in fact, at lower redshift, where direct detection was easier, people like Xiaowen Chen at Chicago and collaborators using Symphony on the VLT, we're finding that these statistical patterns were not holding up in the direct observations that they were able to make of pairs of magnesium-2 absorbers and their host galaxies. So something was still missing in this picture. So I'll just leave that kind of problem aside for a second and talk about some work that has been possible thanks to upgrades to HST. Thanks to the last servicing mission in 2009, some improved deep galaxy surveys have come to be. And one of these I was involved with when I started my first postdoc at Yale. This is the 3D HST survey led by Peter Van Dockum and Gabe Brammer, who's created a really nice package called Grizzly, which makes it easy to reduce GRISM data from which C3. You may have seen it or used it. But this 3D HST survey was designed to use a combination of direct imaging in the near infrared and GRISM, spatially resolved spectroscopy, kind of a poor man's IFU, to make a survey of about 10,000 galaxies in the redshift range of 1 to 3 using the G141 GRISM and F140 direct imaging. And this is just showing which of the emission lines you can see at various redshift ranges using this observational strategy. There's also data from the G800 and the F814 direct imaging, although most of the science relied on the F140 data. So this is what those data look like. It's something that I also worked on when I was at Yale, making photometric catalogs to improve the stellar mass and star formation rate and redshift estimates that came from this survey. But you have this direct imaging paired with the dispersed light from the GRISM setting, which you can then model and look for emission lines to determine the redshifts of those galaxies. So it was a really successful survey. And again, I was kind of being paid to help out with the photometric catalogs, but I got curious, wondering if this could help solve some outstanding questions that the absorption line community had, right? And looking at these data, it was obvious that the resolution and the sensitivity of HST, if you could get enough HST data, could really help us directly detect those host galaxies and understand how the gas is linked to them at redshifts which were notoriously difficult for studying galaxy CGM. So I looked for bright quasars within the footprint of the 3D HST survey, which covered portions of Cosmos and Aegis and UDS and GOODS, south and north, but still only covered 600 square arc minutes of sky. And as a result, there was only one bright Sloan quasar in the entire footprint, which was a massive disappointment until I looked at it, because not only was it really bright, but it also had Keck data and had 3 very strong magnesium-2 systems in the range redshift 1 to 2. So what you're seeing here, just color-coded, are those 3 different magnesium-2 and iron systems in that single, I think this is an SDSS spectrum, but there was LRES data as well. And so that inset that I've been showing you all along is actually the quasar that belongs to this spectrum. And so you can see that there's 3 strong systems in this very interesting redshift range and 4 galaxies within 60 kiloparsecs, which might match to any of them. So using the 3D HST data, we were able to get beautiful segments of spectra for 3 of those 4 galaxies. Actually, we had spectra for all 4, but 3 of them matched exactly to those absorbers that are present in the quasar spectrum. We also have nice morphologies from the direct imaging, and the presence of multiple emission lines in the GRISM spectrum make us absolutely sure that we're not getting the redshift wrong. So those IDs are 100% confident. The nice thing about the GRISM data, because it's kind of like a poor man's IFU, it can also give you a nice spatial resolution of where the emission lines are located. And so we were also able to discern where the star formation indicators were present in the morphologies of the galaxies, and try to distinguish between the presence of AGN and more extended star formation. In each of these cases, because we had also deep photometric data to complement our GRISM spectra, we were able to make precision measurements of the stellar masses. And from the emission lines, we could get dust corrected star formation rates and also star formation rate surface densities from those emission line maps. What was really exciting is that in each of these cases, we found that the star formation rates of these galaxies was high, which certainly agreed with other statistical results, which had shown these magnesium-2 observers are tracers of star formation. And looking at the star formation rate surface density, we could show that in each case that was sufficiently high that it could be explained as large-scale winds being driven out of the disks of these galaxies due to the concentration of that star formation. It was also nice as someone who had worked a lot on clustering to actually make direct measurements of the stellar masses and show that those were also consistent with what we got out of the large scale clustering as well. So all of this was a really nice pilot study to show that, look, we could do this with one quasar in this small field. Maybe we could make a similar survey targeting really high value quasar sightlines that have many observers along the line of sight and very efficiently build up a large sample of deep imaging and GRISM data that could allow us to match galaxies to their absorbing gas at this really challenging redshift. And so I worked with a number of collaborators from Yale and Wisconsin, where I was at the time when we started working on this proposal, to select basically the densest quasar sightlines from all of the SDSS, which we drew from the catalog I'd been working on forever, and found cases where 5 or more magnesium-2 observers were present in the range where we would be able to detect H alpha emission using the WIFC3 GRISM with the same settings as had been shown to be successful from 3D HST. So this is just one of those really high value quasar sightlines. This is the group of collaborators that all came together to put this proposal in. I think many of them have moved since I last made this. John Chisholm is now at Texas, and Gabe Brammer is now at DARC in Copenhagen. So the point of this program was to look at the 9 highest value quasar targets in all of the SDSS. I should mention that even though we were selecting quasars that had a lot of magnesium-2 along the line of sight, all of those absorbers were sufficiently separated in Redshift that we weren't selecting for really high density halos necessarily. We weren't selecting clustered regions of the cosmic web. In total, we were targeting about 60 absorbers, which at the time would have made one of the largest samples of absorber galaxy pairs at this redshift range. So this really was presuming to double the amount of information that we had in this kind of work around cosmic noon. I'm just going to skip the rest of that because I've kind of already said it. It's also worth pointing out that we were targeting magnesium-2 absorbers in a parameter space that better sampled the overall distribution of these absorbers in the broader SDSS. So the contours here are showing where those absorbers are found in SDSS spectra in terms of their equivalent width in magnesium-2 versus their redshift. Now, previous efforts using the BLT by Nicholas Boucher and collaborators had really focused on the ultra strong, these really high equivalent width absorbers, trying to detect in the IFU data the star formation indicators associated with those absorbers, which presumably should have been tracing very, very highly star forming galaxies. And so we wanted to not just select those weird, rare, very high equivalent width cases, but sample more broadly and see what these absorbers are tracing more generally. Okay, so our science questions in getting this HST data were, of course, to find the host galaxies in the first place, measure their star formation rates and star formation rate surface densities to see if these galaxies are all capable of driving large scale winds. And then also ideally measure the morphologies of these galaxies in the direct imaging and their inclinations relative to the background quasars to measure the azimuthal distribution of the gas around these galaxies and try to constrain, if they really are tracing winds, what the shapes of those winds look like at cosmic noon, okay? And then because HST has a very large field of view and the GRISM data should produce redshifts for everything with an emission line in the field, we could also actually look at the environments of these galaxies as well. So we got the time in cycle 21, and this is showing just one of the direct images of one of our 9 quasar targets and the GRISM data that went with it. I should mention that, as you could suspect, right, the GRISM data can be easily contaminated if you have closely spaced emitting galaxies. And so we added to the program requirements an angular offset that was random, so that we would have some chance at getting information back in cases where galaxies light was dispersed on top of other galaxies, causing blending and contamination problems. This ended up being a really good call. This was not something that was incorporated in the original 3D HST survey. And we suspected, because we were looking at such dense sightlines, we would probably be seeing very crowded environments and really need this. And we did. This is that same field now with circles indicating the galaxies that we have well-determined redshifts for. The 2-dimensional GRISM spectra are shown in that kind of middle panel, and the 1-dimensional versions with contamination cleaned up are shown on the far right. And hopefully I can convince you that we see real emission lines and in many cases, multiple emission lines, making our redshifts really highly confident. Now, every galaxy in this field that's circled with a solid circle is one that not only has a good redshift, but actually matches to absorption that we see along the line of sight in the quasar. The galaxies that have dashed circles have well-determined redshifts as well, but we were unable to match those to absorption. Yes.
The pre-imaging, did that exist or you took that? Did you have that before?
No, we didn't have it at all. Yeah. I will say a few of these fields have been followed up with MUSE. So Nicolas Boucher does at the same, we were basically doing this at the same time. So independent of one another, we had selected some of the same sightlines for the same reasons. And so 3 of these fields have MUSE data also. But this is direct imaging that was taken for this program.
Yeah, so the selection was really just that 1D spectrum from.
Yeah. So the results were really kind of the best we could have hoped for. So almost 90% of the absorbers could be matched spectroscopically to galaxies in these fields. This was like doubling the rate of detection for host galaxies that had previously been done using Symphony data on the VLT. So this was a major advance. Now, around the same time that we published this, people were publishing similar results with MUSE. So now you can do the same thing and we get consistent results. So groups that have been going after these same kinds of questions using MUSE are finding again about 80 to 90% success in detecting the hosts that go with the absorbers. And the ones that we don't detect aren't ultra strong. Okay, they seem to just be normal weak absorption in the middle of our equivalent width distribution, which suggests that we're not missing things because they're right on top of the quasar and obscured by the light of the quasar itself. And just to prove this to you, I can show you the 9 quasars at the centers of each of these fields. Only one, the one in the middle right-hand panel, we had to ditch completely because that field was too crowded and the spectra all ran into one another. But 8 of the remaining out of the 9 were all used in the analysis, and only a few of them have indications of resolved light that seems to have been missed by our redshift survey. And of course, those could explain the few absorbers that we failed to match. So just to show you the field that we ditched, it's a shame that we couldn't get it. Actually, this is one of those MUSE fields. And there are just 3 quasars within 2 arc seconds. Sorry, 3 galaxies within 2 arc seconds of the quasar. And it was just a disaster. Both orientations were contaminated, and so we had to throw it out. That's not to say that you can't resolve galaxies and get good redshifts using this method within an arc second or 2 of the quasar. In some of our fields, we were able to successfully do that, which is what's shown on the left. All right. So just to quickly share some of our results. Like I said, because we could get redshifts for all of the galaxies with emission lines in the field, we were able to show that about 40% of these absorbers actually match spectroscopically to multiple galaxies. This probably isn't a surprise because galaxies group and cluster together. What we did find is that the galaxies that match to multiple, the observers that match to multiple galaxies are also skewed towards higher equivalent widths. Again, this isn't probably a surprise since a sightline probing through multiple galaxy halos should be passing through, multiple clouds of gas, which would create a larger velocity dispersion and a larger equivalent width. So this is also consistent with some recent results from groups that are using MUSE. And so it's nice to see, because each of our samples is smaller than we'd like, that we all still are seeing approximately the same thing. I should also mention, it's possible that intergroup gas could also be showing up in our equivalent width distribution in the cases where we match multiple galaxies to a single absorber. And there's plenty of reason to believe that that should also be playing a role. Because we were able to measure the star formation rates and star formation rate surface densities for galaxies with and without absorption, we could also show that the galaxies matched to absorption had preferentially higher star formation rates and star formation rate surface densities. Again, consistent with this idea that magnesium-2 is associated with star formation and probably large-scale outflows driven by that star formation. So I want to just kind of wrap up by telling you about what I think is the most exciting result from this work, which was only possible because of my student, Samantha Creech, who recently graduated from UNC Asheville and is now a PhD student at Utah. She did a really amazing job gal-fitting all of the galaxies in these fields and carefully measuring their inclinations relative to the background quasar. And what she was able to show is the azimuthal distribution of the gas in terms of the angle with respect to the major axis of the galaxy. So what we could see, again, remarkably, because we're really borderline in having enough data to show this in a statistically convincing way, was a nice peak close to 60 degrees, which is exactly what you would expect if you were measuring outflows that were biconical in their spatial geometry and also denser along the edges than in the interior, which is also what you expect from simulations of these large scale winds. So we see a little excess along the major axis, which again is what you would expect if gas is also correlated along that major axis too. And again, we had just enough data to try to answer where do those outflows end. And this is really, really tricky to do with these redshifts. But we argue that we're seeing that excess in absorption consistent with biconical outflows extending to approximately 80 kiloparsecs around these galaxies, which are on average about redshift 1.2. So here you can see those two distributions of the azimuthal angle, one truncated at 80 kiloparsecs and the other showing gas at larger angles. And there certainly is a more striking peak around 60 degrees in that gas that's within 80 kiloparsecs. Now that actually is exactly what the illustrious TNG simulation predicts for galaxies of approximately the average mass that we're looking at, which was again just a really nice surprise. And it's also, good news for their simulations. This is showing the same thing, but in an angular plot showing where each of those detections was found. You can kind of see here the excess within about 60 degrees of the rotation axis of the galaxy, and also how the gas that we detect along the minor axis here is also tracing preferentially higher star formation rates. All of this is consistent with large scale star formation driven outflows. Okay, so this is my second to the last slide. I just want to show you that there's still more that we could learn. Those same illustrious TNG simulations predict how the extent of these large scale winds should be different for galaxies of different mass. Unfortunately, we don't have mass information in these particular fields. We only have single wavelength photometry and would like to improve that with additional follow-up in different bands. So we're in the process of trying to get that through the HST TAC so that we can start to answer questions like, does the extent of the winds depend on mass in the way that simulations predict? Okay, so just to wrap up, I'd like to make the point that these very large samples of quasar absorption lines which we've been building up for decades, have really started to reveal some interesting information about galaxies at intermediate and high redshift. Those revelations have come both from statistical analyses, indirect measurements of what the galaxy hosts of those observers look like. And also we're seeing from direct detections that we can, at least in composite, see how this gas is distributed spatially around galaxies at redshifts where this is really, really challenging work. I'm encouraged by the future of this field as well. I think we still have a lot to learn about these gaseous processes driving galaxy evolution. There's still a lot of science that can be extracted from the galaxies and quasars in the EBOS sample. So I'm in the process of working on that with some collaborators, but then of course I'll have JWST and future larger deep galaxy surveys. And so I look forward to hopefully more years of continuing this as well. So anyway, I will leave it there. And if you have any questions, I'd be happy to take them. Thanks.
Thanks, Britt. Do we have any questions from the audience here? Yes.
So I want to make sure I'm connecting the dots right on the image you showed from HST. There were some galaxies that didn't have a corresponding observer. So are those referentially things that are pointing their major axis to the quasar, or are those maybe things that are behind the quasar, or do you know what's up with those?
So that's a really good question. I think in that azimuthal distribution plot, we do see the distribution for galaxies that aren't matched to the gas, and that does appear to have a flatter distribution. It's maybe not the clearest way of showing that, but we have looked into the inclinations of those galaxies relative to the quasars. It could be a lot of things. It could be their star formation rates. We know those are lower on average, but certainly, yeah, if they didn't have the right inclination, we might not detect the gas that's being blown out of them. That's true.
Okay. Anybody else here? Let's see if there's anything online.
How does the absorption spectrum help with estimating the stellar mass? So it doesn't, unfortunately. Early on, this canonical idea of explaining absorption line velocity dispersions as a measurement of the halo mass of the galaxy has been largely turned on its head through clustering measurements. So it turns out that observers that have really large velocity dispersions, at least in magnesium-2, tend to be tracing lower mass galaxies, at least in their average clustering, relative to narrower absorption lines. And that can be explained as the gas not being virialized, but maybe your line of sight is passing through an outflow that has a large velocity dispersion, and that creates the width in the absorber that you see. But yeah, that was a surprise in the early 2000s when we started having enough of these absorbers to actually measure the average halo masses. That was not what was expected. And outflows is a way of explaining how it's possible that gas with such a large velocity dispersion is associated with, on average, halos of lower mass. Yeah, so to know the stellar masses for these galaxies, we really need better detailed SEDs in the infrared.
I would actually ask, so is that something you can get with JWST, or is that just?
Sure, yeah, someone will give it to me. Yeah, but we actually, so I've teamed up with Nick Labouche, and we're trying to convince the TAC that these are legacy fields. It's hard to find quasars this bright with this much absorption, and that, if we make deep fields similar to Cosmos around these quasar targets, then we can get those well-determined stellar masses to really learn more. But yeah, but JWST would also give us that same information. Yeah.
So my
Oh.
phone overheated and closed the Zoom.
Oh,
So
no.
Perhaps we can stop sharing here
Sure.
and check the participant list and see if anybody's got their hands raised or there's anything in the chat.
Okay.
Okay, Brian.
Yeah, so hey Britt, so it's great to have you back, and great talk. So I guess my question sort of follows on to the last. So the picture I'm getting is that what you're seeing are these kind of outflows from sort of starburst like galaxies. Speaking of the velocities, is there any way you can look at sort of the energy budget to get an idea of the way it's powered through the starburst versus the energy in the flows?
That's a good question. I'm not sure. Yeah, I'm not sure if we can get at that information.
Because I guess you need sort of densities and velocities as well, and the star formation rates. But for the outflow, you need to know densities and velocities and something about how big it is.
Right. Yeah, I mean, I guess we need the mass loading factor. So that kind of information, I think we could get through down the barrel measurements of those galaxies. So Christy Tremonti and I are working on doing that with some of the EBOS galaxies in early stages. So maybe ask me in a year and I have a better answer for you.
Sounds good, thanks.
Yeah.
Okay. Let's see. Look at the participants list here. Okay, do we have any other questions online? Yeah. Okay.
Why magnesium 2? What is it in a good spot in the spectrum? There's not a lot of other absorption near it, or it's the doublet. What is it that makes it? Why do people always use this for outflow tracers and absorption?
Well, because it traces outflows for a start, but the reason we have so much of it is because it has a convenient wavelength,
Yeah.
right? So in optical spectra, we see it over a really large range in redshift, like 0.3 to 2 and maybe 2.2. As long as the quasar is behind it, we have a chance of picking it up. And I should say, we limit our search to portions of the spectrum that are outside of the Lyman alpha forest, because with Sloan resolution, it's really hard to detect metal lines in the midst of all of that hydrogen. So because the line is found at 2800 angstroms, it's picked up at lower redshifts outside of the forest, which makes it really easy to find over a large range in redshift in these optical quasar spectra. So, and there's a lot of it. I mean, it's just a common product of star formation. And so if you're passing anywhere within about 100 to 150 kiloparsecs of a galaxy, you're probably going to pick up some magnesium 2. If you're if you're sensitive enough in your signal to noise and your resolution, you'll almost certainly detect something. With the exception of really massive hot halos where we don't pick up that gas because it's cold-ish. And so, although there are exceptions to that rule as well, 10% of LRGs do also have some magnesium 2 in their circumgalactic medium. But it's less common around really massive galaxies, presumably because of the virial temperature.
I was going to ask, so does that sort of give you a window of masses on which it's really sensitive?
Yeah. So yes. So we tend to pick it up around halo masses of 10 to the 12, which is also kind of an average mass of a galaxy, which is suspect, right? But yeah, Jeremy Tinker and Xiaowen Chen have a nice, completely undercited halo occupation distribution model just about magnesium 2 gas which makes really nice predictions about where you should see it in a range of halo masses. And because of the temperature at high masses, you would be surprised to see it. Yeah.
Yes.
Except for the redshift, like the distance of the galaxy, what information would be absorbed in the spectrum give us amount of that galaxy?
So if you have neutral hydrogen measurements, you can do more elaborate modeling of the ionization conditions of the gas. For most of the SDSS spectra, the observers that we detect are saturated, and we also don't have neutral hydrogen columns to constrain their properties in most cases because of their redshifts. So the short answer is in the data I'm using, we don't have a lot of really precise constraints on the physical conditions of the gas, but if you have better spectra and less saturated absorbers, you can use cloudy modeling and really learn a lot more about the kinematics and the temperature and density of the gas. But unfortunately, we don't have the resolution to do that. Yeah.
Is there any way to like know how old the galaxy is, or just like looking at the absorption spectrum, or is that something?
I would love to know that. Okay, I think the owl is alerting us. Yeah, so the age of the gas. So I think that's the information you could get from a direct spectrum of the galaxy itself. I'm not sure that the gas in the CGM can help you, or what we find is that if there's magnesium too, it still has some active star formation going on most of the time. So in that sense, it is kind of telling you at least about the the recent star formation activity, but not really the age. Yeah.
We use the calcium H&K depth to tell star age. Okay.
Yeah. So if you have the spectrum of the galaxy, you could use the Balmer break and the H&K lines to estimate the age. But with the spectra that we get from the GRISM data that I showed, it's really just a tiny little wavelength window. And so we've picked that window to look for H alpha emission because we primarily care about the star formation indicator. But you could also pick that window to look for the Balmer break, and that might tell you the age if that's your primary question. That's a good idea. Yeah.
I'm wondering if so once you've sort of established the redshift from the magnesium spectrum, can you search for lines from, I don't know, our process elements or things like that to see if you can measure, or is that just hopeless?
It's not hopeless in the stacks.
Mm-hmm.
Yeah, so you could look at the average abundances of weaker lines, and I'm trying to think if anyone's done that. I'm not sure. Yeah, but we have a very agnostic approach to detecting lines. And so we look for something like 60 different ions. Most of the time, if you pick up something rare, it's just a chance coincidence. It's a line that's in the right place at the right time and not really the rare thing that you might be looking for. But stacking absorption systems would be the best bet. Matt Pieri does some of that work measuring abundances, and it could be that someone's done that, but I'm not sure. Yeah.
So stacking seems like you might be able to pull it out.
Yeah.
Yes.
So the width of the magnesium lines that we detect, does that tell you anything? Does it go about the gas?
Yeah, so the width of the line, like I was saying earlier, was since Bacall and Spitzer first made this kind of cartoon idea of what's causing these absorbers. Their idea was many clouds of gas in a virialized halo, which are intersected by this distant quasar, right? In that case, the equivalent width of the line, as long as it's velocity dispersion dominated, could be telling you about the mass of the halo. But for reasons we were talking about before, at some mass range, the halo gets too hot to support this cold tracer. And so then it stops making sense as a measurement of velocity dispersion. So the fact that we see, really broad, high velocity dispersion magnesium-2 observers around really low mass galaxies can really only be explained if that line of sight is probing through a wind with some opening angle and kind of catching clouds along the way, creating that large dispersion. So that's kind of the new paradigm for interpreting these really broad lines. I say broad, I mean, they're all pretty narrow, but yeah.
Okay, do we have any more questions? Going once, going twice. Okay, well, let's thank Britt again.
Thank you.